the chromophores. This is where things actually get interesting, in my opinion. So the chromophore elements are the reasons minerals have color. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different elements that are transition metals, ranging from, on the periodic table, 21 to 30 in atomic number. And they include Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Those are the 10 that are the big color causers for minerals. And the cool thing about these things is that they don't actually produce the same color in every mineral. For example, chromium can produce reds in one mineral and produce a green in a different mineral. It's very, very strange. And that's getting into even more complexities and probably beyond the scope of what I'm going to be talking about tonight. So back to this. This is the table, the periodic table. If you want, this is from, I don't remember where I got this. I think it's ptable.com. Yeah, it's ptable.com. The link is here if you guys want that. It's a dynamic periodic table, and I really, really like using this for a lot of stuff. I just screen capped it and then circled the transition metals that I needed to. So these elements only need to occur in very, 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 very small quantities, such that they're 0.1% weight percent of the total mineral's chemical composition. So it's negligible. They're very, very negligible, such that they're not in the chemical formula. They're not written in the chemical formula of the mineral. They don't matter except that they actually make a color. They do matter, but not for the chemical formula. They don't. They're not enough. It's not enough. So an example of one of these chromophores might be iron in amethyst. Iron gives amethyst its purple color. Now, if iron is irradiated or literally it undergoes radiation, then the mineral will turn into this yellow color, in which case it's then called citrine. Well, different chemical bonds can also control a lot of this as well. The chromophores are only one component of color in minerals. There are many others. There are a variety of these elements that can create a variety of different colors in different minerals. So erythrite, Hikari, one of your favorite minerals. Guess what its color red is? The violet red that it comes from? Guess where it comes from? The element cobalt. The element cobalt produces the violet red in erythrite. It also produces blues in other colors, or in other minerals that I've seen. Really quickly, let me just show you my erythrite, which has arsenic in it as well. It's an arsenic-bearing mineral, so I'm not going to touch it right now. I'm just going to put it out here under the camera, nice and centered for you guys. Now, oh gosh, it makes it look kind of brownish. All right, there's this picture here. This is erythrite, the mineral. It is got cobalt in trace amounts, such that it produces this reddish, magenta, violetish color. No, the red on Mars is actually because of iron and the oxygenation of the iron, not because of cobalt. But it's cobalt in erythrite, in this specific mineral. Now, it's because of this and the other surrounding elements in it that it gets this color, and there's a lot more complexities that go into it. It's not just the chromophores. Chromium, on the other hand, can produce the color orange-red in the mineral chrosoite, but I don't have a sample of that. It's a gorgeous mineral, but it is a bright red. Conversely, chromium is also the reason fuchsite is green. So it's quite strange when it's housed alongside of different elements, how very, very, very different it can be. Let me just sharpen this up a bit. It's a bit better. There we go. This is a type of muscovite. This is actually a mica. I do have rhodochrosite, yes. But this is a type of chromium-bearing muscovite, and it is therefore actually green because of the chromium. Whereas in chrosite, the chromium, chromium is a chromophore. It's one of those transition elements that provides colors in minerals. can produce the bright red and chromophore. Moving on, we've got copper. Copper produces the blues and the greens in malachite and azurite. So we've got malachite here. We've got azurite next to it. And these are both copper rich carbonates. They're very similar in chemical composition and can oftentimes alter to one another. Usually it's usually the azurite is altered to malachite is what I've typically Iron seen. Can make a lot of reds in minerals, of course, like hematite. It can make the purple in amethyst purple. It produces the red in limonite, which is an hydrated iron oxide, whereas hematite is just regular iron oxide. It's not hydrated. Manganese produces the pink color in rhodochrosite, another carbonate. This pink here is because of manganese. Again, manganese is a transition element. Here's a nice cleavage plane. Isn't that pretty? Isn't that nice? Isn't that so nice? Yeah, this is a really, really nice specimen. I love it. I really like this. Rhodochrosite's a bit spendy. And the thing with carbonates is they are not great for jewelry because they're so soft usually. So they'll scratch very easily, and they are susceptible to anything slightly acidic. So they'll dissolve almost instantly. Let's see, nickel. Nickel produces the green color of annabergite, which I don't have a sample of. So let's look it up. Annabergite. Mindat usually has some really nice images. So this is, oh man, we have looked at this before. So nickel is the chromophore, i.e. the transition element that produces the green in annabergite, which is really, really pretty. Let me make this big. Big. We need you big. Actually, I didn't actually need to do that because I can just do this. That's really pretty though. It's translucent, nice vitreous luster. Again, that has to do with the light reflecting off of the plane. A picture of annabergite up here because we're talking about why minerals have color. We're talking about the 10 different transition elements on the periodic table, numbering 21 to 30, that are called the chromophores in this case. They're only referred to that typically in regards to colors in minerals. I've really never heard the word chromophore being thrown around in any other circle. I don't even see it in any chemistry literature. It's not in geology literature strictly. And it may not always be the case, but nickel in this case is the transition element causing this to be that bright green. It's really, really quite cool, I think. So that's annabergite. It's got nickel, arsenic, oxygen, and 8 water molecules per chemical formula. Crazy looking yellow and green thing initially formed around the yellow area. It might have. I don't know. That looks like it to be the nucleus. Let's look at it. So when a mineral grows, it does have to nucleate onto something, either it be in a solution or in a magma body. Either way, there needs to be a nucleation site to start the mineral growth. It could be that this is what it started on. I don't know what this is. It's different than the annabergite in shape and color. I don't know what it is. In fact, you can see more of that here. Wouldn't be surprised if there's sulfur in it. All right. Now let's look at other minerals and why they are colored the way they are. Uranium. Yeah, that's a really good one. Uranium produces a lot of those bright yellows, almost greenish yellows, almost glow in the dark yellow that you see in like uraninite. Tons of uranium-bearing minerals. Zipyite is the mineral that this one suggests, but I want to look at it. So this is an example of a uranium-bearing mineral which is again a transition element. That is one of the reasons minerals are colors. Oh, vanadinite. I have vanadinite. Vanadium. Vanadium and vanadinite produces a red, but it can produce green in things like hiddenite, which is a variety of spodumene. So this guy here has vanadium in it. It's actually grouped into the chemical group of vanadates. It's grouped with the phosphates and the arsenates as well. They aren't very big groups of minerals, so that and because of their structure being similar. They're grouped together oftentimes, but this is a vanadate called vanadinite. Super fancy name. Super clever. Nice vitreous hexagonal crystals. You're kind of seeing the side of the crystals, not the tops. If you could see the tops, you would see the hexagon shape, or at least part of it. But these are really, this is a really nice sample. You see that nice red. Again, because of the transition element vanadium, you get that red color. And you get a very similar reddish color because of iron in other elements or in other minerals. So it's, you know what, I'll just show you a picture of hiddenite because my hiddenite's super tiny. It's a really special piece. But hiddenite is another one with vanadium in it that is not red, but instead green. And it looks like that. So these chromophores, man. So this is actually a feldspar. It's a silicate, a lithium-bearing silicate, but in trace amounts, there's vanadium in it that can cause the green. In fact, there are samples of this spodumene that can have chromium in them as well that is green. So you can have both vanadium and chromium in this in trace amounts that causes this element, this mineral to be green. I don't remember which of these two. Either I don't know if it's the chromium variety of hiddenite or the vanadium variety of hiddenite, but one will actually fade in UV and the other will not. And that's how they know it's from the location of hiddenite or not. Because the locale at hiddenite where they originally discovered this mineral, they then found others elsewhere, and the others elsewhere fade in UV. So they know they're not the actual location. You know you're getting the actual thing from hiddenite, North Carolina, if you get the ones that don't fade in UV. But I wouldn't recommend buying one and seeing if it fades because, well, you're kind of ruining your mineral. Oh, another cool thing about this mineral is it's pleochroic. So it actually looks brighter green down the C-axis. So if you were to look at it from the very top, if you were to take it instead of looking at it on this side, but look at the top down, it would look like a much more bright green than it does on this side. My tiny sample in person, you can see that. On the camera, I'm having a harder time showing the pleochroism. It's just doesn't show up as well.